And so, talking about the architecture of Q has evolved a little bit, and in part due to our extreme testing that we've been doing on testnet in terms of just overall improvements that have happened more broadly in the research space, and ultimately has culminated into what this architecture is today, which is at the global level, every single node is maintaining a collection of global synchronized commitments, and this is about 19 kilobytes of data. 19 kilobytes of data is very easy for every single node to keep track of and keep up to date. This isn't something that we run into scalability issues with because it's something that, one, it propagates every 10 seconds, and two, it's deterministic in nature, so it's very easy to avoid any sort of conflict resolution problems. And then from those global synchronized commitments, we actually create the collective data shards of the network. And these shards are represented as a tree. If you are familiar with the structure of Ethereum's world state tree and account tree and all the other trees that they use, they're all the same kind of tree. It's a Merkle-Patricia tree. And a Merkle-Patricia tree is a radix tree that is essentially from the root of the tree, you have 16 elements, and they represent the nibbles of the byte, which is 0 through 9, A through F, in terms of hexadecimal, and then it branches out into the overall leaves of the tree. We do something similar, except ours is a vector commitment tree or Verkle tree. And what that enables us to do is two things. One, we have expanded the branches out to 64 individual slots instead of 16. That has proven to be the most efficient in terms of computation for us. But two, when you create a proof for a Merkle-Patricia tree, you have to actually include a lot more data into your overall proofs to prove that data exists. And it ends up being roughly, with the current state of the network and how large it's grown, it's roughly about 1 kilobyte of data that you have to provide for proving any one thing. And with a Verkle tree, we actually only have to provide a handful of elliptic curve points, which just serves as the basis of proof of data on the network. And by consequence, that means that transactions are lighter weight, proving any data on the network is lighter weight, and overall, this can scale out much more broadly. One of the things we also do with this core tree, and why this is important the way we've structured it, is that the nature of how this is structured provides additional metadata as you go up further in levels. So on the tree, you have essentially a bit of data that says how many leaves are underneath that branch, how big the overall data is underneath that branch. And from that information, that actually tells us when we should break out into a new shard. So one of the things architecturally you see in very large-scale applications that aren't crypto-related is you'll see them have a partitioning scheme that basically pre-partitions the data into logical partitions before it actually is used into individual partitions on whatever that application is. We do the same thing with our shard trees. Again, bear with me, still dealing with the flu. So from this tree, we end up having a bunch of data that is essentially constantly keeping monitoring of how much data it's contributing from that branch level, and also where in the position of the tree that it is. And so by consequence, workers, once they've reached a certain threshold, can break that data out and say, like, hey, this branch of the tree is now 2 gigabytes of data instead of 1 gigabyte of data. I'm going to split my workers out and cover those 2 individual branches instead of having a worker covering just one, because this is going to be more viable. And not only that, it also gives us the ability to very easily reason about how multiple shards can be proven over in one single step, because that root of that branch, not the root of the tree, the root of the branch, gives us the ability to, at that exact position of the multiple shards, create a proof that constitutes that one block of shards. And that's just the tree structure. Below that, we have a verifiable delay function that's utilized to essentially dictate the operating clock of the network. You can think of it as like a periodic settlement of data. And additionally, a periodic proof that that data has been held by the individual nodes that are providing access to that data. On top of that, the data itself that lives on the network is utilizing what is called verifiable encryption. So when you're putting data on the network, you're actually encrypting this data in such a way that you prove, one, you have the relevant key to this data, or you have provided a public key relevant to somebody who should have access to this data, and two, you have provided sufficient proof that this data is encrypted such that whoever that key holder is can reasonably decrypt it. And then as we descend further down the structure of the overall architecture, we utilize a traditional log-structured merge approach with how data is stored for the most part. We actually just swapped out the LSM approach for the trees themselves by moving to flat files for the tree metadata. It just ended up being more efficient, and it also was not like when we were originally trying to store it, it wasn't cooperating well with our overall LSM-based approach. So that itself is in separate flat files, but the overall shard data itself, the vertexes of the hypergraph, the actual underlying verifiably encrypted data, that all lives in the LSM style database. And then on the execution side of things, we have essentially the primitives that are required to provide private retrieval of data, private execution of alterations to that data, or at least evaluations of that data. And as we move forward and introduce even more primitives, we'll be enhancing what we can do on the network to greater degrees. So when we talk about how we're enhancing that, we talk about what the nature of the network is like in the first place. And from the Dawn era, we had introduced a lot of unique core concepts to the network, things that other networks were only slightly doing or doing differently. In the case of the peer list, that one's actually a little bit commonplace for all of them, but it's just important to know that we have this idea of a globally shared distributed hash table of peers. But essentially our sequencing of data through the master clock, the data proof clock, the secure message channels, those have already popped up in use with Quorum. The key manager, which is how we're essentially providing a peer level key and then a prover level key. That prover peer separation is something that'll be very important for keeping essentially the recipient of a reward in cold storage without having to constantly reveal their key material. And in fact, they don't even have to reveal their public key if they're just providing an address. Our original ceremony application, which was demonstrating our ability to calculate this MPC evaluation, is essentially an extension of our original Powers of Tau ceremony. The execution context itself, which is what we thread through to the overall master and data proof clocks, and then the primitive storage layer itself, that's something that we've rapidly iterated on and enhanced as we've gone along. And we've now entered this phase called Dusk, which is the 2.0 release and then subsequent 2.1 release of the network. And this release has been a bit tumultuous as we've been iterating and evaluating and revisiting some of our initial assumptions. They say the line goes, everybody think they got a plan until they get punched in the face. And we definitely got to get punched in the face a whole lot when it came to how our assumptions were tested against the reality of hundreds of thousands of nodes being flung at the network instantly. We really had to test problems of scale that other networks just haven't. And a lot of that comes down to the basic principle that we've done differently that other protocols besides Bitcoin haven't done. And it comes down to this. We don't have a token generation event. We don't have a pre-allocation or distribution to insiders or VCs or people who are doing marketing or those awful KOLs. We didn't do any of that. And instead, we strictly did a fair launch. If you launch a node and you participate in the protocol, you get rewards relative to the rules of the protocol. And by consequence, that meant that a lot of people immediately jumped in and started, of course, running their nodes. And so this, unfortunately, has resulted in, we had a lot of problems that we had to solve at scale that other protocols probably never even will. But the Dusk series of releases has resulted in us bringing out these very important elements that are essentially the foundation of what this network will be capable of doing. And so when we talk about the Dusk release, it is the combination of 2.0 and 2.1's work that is coming into place, like 2.1 being launched very soon. Again, I learned a lesson about providing dates. That's a terrible idea to do because, like I said, plans change when you have to deal with unexpected surprises and black swan events. And so our 2.1 release will be providing some of the rest of these things, specifically the secure private routing, the OT circuit compiler. Outside of that, the schema repository is going to be set up this Sunday so that we actually have a generalized basis for doing the broader structured data settlement on the network and how nodes will know how to interact with it without having to actually see the data itself. And then we'll also see the first hypergraph applications be deployed to it, specifically the token, which will be the continuance and essentially the main fork point of 2.1. But the oblivious hypergraph, we're actively testing through that right now. That's been quite a substantial amount of churn in our 2.1 testing because like I said, we've learned some very powerful lessons about how much data our underlying log structured merge database can handle and how we can work around some of those problems as they pop up. Now, this is a lot of things that are important to understand if you want to be a developer on this protocol. But if you want to be a developer on the network and not think about how the protocol is doing these things, the next question that tends to naturally emerge in people's mind is, well, what can come from that? How do we build from that? Like what, is that, say I'm a traditional developer, I've been launching applications in the Web 2 context for a long time. How do I translate these ideas that I've accumulated into this Web 3 world? And people will often find issues doing that with other networks. Like, for example, if you're wanting to launch a decentralized application on Ethereum, you have to construct an application that is built using the special domain-specific language native to Ethereum's virtual machine. Commonly Solidity, sometimes people write in Viper, but it's a little bit less common than Solidity. And that only relates to how data is explicitly stored on the network. And Ethereum can't hold a lot of data. It's very expensive to store a lot of data on the network, especially if you're storing it as call data. But even if you're storing it as the KZG blobs that are now supported on Ethereum, it's still very expensive. And so what often happens is it ends up being a register of reference. Like, for example, when somebody creates an NFT, at the end of the day, it's not that decentralized. They put an NFT on the protocol through a deployment of a smart contract that implements the NFT standards, but the actual image data of it is almost always offline, like off of the chain itself. It's somewhere else, usually on S3 or IPFS. If you are trying to do anything particularly special about how that's being managed, oftentimes there's a lot of tooling that is centralized in itself. The indexers of content, the services that determine, like, oh, these users are holding these NFTs and displays it in your wallet. These are all centralized services. These are not questions that people are, like, your wallet is not directly talking to the Ethereum protocol. It's talking to some third party's API. And so that is one of the most critical things to think about with how Web3 development is currently done, is a lot of it isn't as decentralized as you think it is. And so revisiting that entire set of assumptions in the Q space is thinking, well, how do I actually use these services if they are decentralized? Because using Ethereum is very hard for the actual decentralized portions of things. And the answer is you don't make it hard. You make it exactly as intuitive as it has been. And so building on top of Dusk, the things that Quilibrium Inc. has been doing is building services that are very familiar. And so that's been building an S3 compatible API, the KMS compatible API. These things are some of the most heavily used products in the space of crypto specifically, and it has been relying on centralized providers to provide those particular services. So instead of deploying a smart contract to Ethereum that has a bunch of like link references for image data to S3, you can instead utilize Quilibrium's S3 compatible API, put that data on a decentralized protocol, and then you can reference it the same way you had been, and now you actually have a significantly more credibly decentralized product, whatever it is that you're building. Same thing with KMS. A lot of people have been relying on wallet as a service providers, and a lot of them are not being very honest about the nature of how wallet as a service works for their infrastructure. It's very frequently behind a centralized, trusted execution environment that takes key material and actually does the signing operations as a unitary actor instead of a cooperative protocol where one person's holding a key, the infrastructure is holding the other key, and it works together. But on top of that, we're more broadly going to be providing other additional APIs that are compatible with existing services like Redis compatibility, CQL compatibility, Lambda style compatibility, and that's a bit longer out, but these things are very crucial for actually decentralizing the broader web. And instead of getting into like pissing matches on Twitter about how decentralized a protocol is versus how, VC captured another protocol is, we're instead focusing on an entirely different domain of people. We are willing to work with and do work with crypto projects to help them actually meet their needs, but we're coming to them more in the same style that a Web 2 provider is, in the sense we're coming to them about what problems we're actually trying to solve, and not trying to just like tick a box on how this somehow makes something decentralized. We're actually trying to solve their actual problems that they need to solve. Then from this first generation, we move into the second generation of broader services that we intend to offer. And so in that, we end up with a streaming video store, streaming audio, image store. Those three things are essentially building on top of the existing object store that we're going to be exposing, but they provide really important attributes that aren't necessarily in those natively. A lot of that is compliance related, but that's still something very crucial that companies pay a good amount of money for, because compliance is something very, very, very important to businesses. Regardless of the ethos of a particular project and what they say, they still have to be beholden to the law, and that's something that we are very dead set on delivering in a way that still provides privacy. And then on the broader end of things, you've already seen, most of you at least, have already seen the machine learning runtime that we've been toying around with and experimenting with and getting early data on. Our scheduled tasks surface area, which allows you to evaluate functions on the network on a recurring basis, something that other chains do not let you do. And then also the meta virtualization layer, which is essentially taking what would be like EC2 on Amazon, but putting it on the network. And that's going to be a significantly, it's a larger lift for the protocol, but it's something that is going to be a real game changer in how applications are deployed in a decentralized way. And that's essentially what we've been putting together. That's what we've been working towards. And so if you're trying to ask yourself, how things are being done for Quilibrium, and what is our intentionality of the protocol, and what we're more broadly working towards as a fulfillment of our overall goals, that is essentially what we're doing. We are trying to reshape the internet by essentially rebuilding some of the most infrastructure critical pieces from scratch, but doing so in a way that people are actually going to be familiar with how to do it. Right now, we haven't had so much luck with trying new things and introducing new technologies and getting people to adopt it, which is why a lot of new chains that introduce their own new DSLs often suffer, and that's what we want to avoid. So, the last thing that I wanted to dive into for tonight was talking about the nature of how shards work on the network. And that's something that is, like I said, it's based on our overall tree structure, but I want to dive into deeper detail about how that actually plays out with the overall structure of the nodes on the network. And so there was a diagram that I had posted because somebody had a question about the way that shards work and who is working on what in terms of overall components of the network. And so this diagram was created and was posted in the Chinese Discord channel for the Quilibrium community. And some people saw that and were like, wait, where was this discussed? And it was just an explanatory diagram. And so instead, I'm going to actually walk through what this means because people had a lot of questions about that with respect to sharding. And so, like I said before, shards on the network are logical shards. There is a physical separation to it when you start to get into how those shards are held by the network. So to give you kind of an idea of this, let's say that we have an application that holds S3 style objects, because that's something that we obviously will be having. Those objects are essentially going to be vertexes on the hypergraph, and a vertex essentially becomes a singular leaf on the overall proof tree of the hypergraph's underlying storage data. So to break this down in terms of detail, I'm going to describe what is the developer-facing view, what is the underlying logical/protocol facing view, and then what is the actual implementation and how those differ and how you can reason about them. And so talking about things from a developer-facing view, let's say you are structuring things out as objects, like I said on S3. From a developer-facing view, you would actually have, well, simply an object. Like it would just be a structural object. That object might have some useful properties like the underlying data, maybe the metadata, talking about content types, whether it resolves to a publicly accessible bucket, just things like that. You're essentially defining that object and then storing it on the network. So from a developer point of view, I am somebody who wants to put objects on the network, and I don't have to think about anything else. And then from a protocol-facing view, let me clarify this so later if somebody sees a screenshot or something from this, it is specifically like from an S3 point of view, an object. From the protocol-facing view, this would be composed of essentially either one or multiple vertices on the hypergraph. That hypergraph has a structure of essentially different layers. You have the global shard commitment level, which is essentially 3 positions of the overall bit mask of the global level. Then there is a level 1 which defines the app address, or sorry, a level 2 which defines the app address, and then a level 3 of that which is the overall tree position under that application. And then the last portion would be, from an implementation perspective, it would be the vertex adds set of the specific app shard of the hypergraph. And so that would then land in the overall tree of the network. So now let's talk about this in reverse, how this actually plays out. So when you add data onto the network, there's essentially 4 sets of data that you are dealing with respect to the hypergraph. There's vertex adds, vertex removes, hyperedge adds, and hyperedge removes. If you are familiar with conflict, I can never remember what it stands for. It's like conflict resolution or conflict-free resolution data types, CRDTs. If you're familiar with the parlance of CRDTs, this set notation will be very familiar because it's essentially two-phase sets. And if you've ever seen any of the mathematical proofs around building graphs in a CRDT basis, they frequently use the model of a two-phase set, which provides the vertexes and the edges. Or in our case, since it's a hypergraph, the vertexes and the hyperedges. But we're starting simple here. We're strictly talking about how objects get resolved on the network. So if you're putting an object, just a simple S3 style object on the network, there's a few limits you have to keep in mind, which is a vertex can be no greater than 1 gigabyte in resolved data. And so what does that mean? When you have a block of data as an object, it could potentially be many sizes that could be potentially over 1 gigabyte. And so by consequence, you may need to break it down into smaller pieces. But on top of that, it has to be stored in a way that's native to the network. So now you have to do 2 things. You have to break it apart into at a best case scenario, the largest size chunks that you can be allowed to place on the network. So say this is 1.5 gigabytes. For the sake of being easier to pool, you would want to have oh, yep, okay. You'd want to have a 0.75 gigabyte pieces. Like I said, bear with me, dealing with the flu. And then those pieces would then be passed through a verifiable encryption process. Verifiable encryption is essentially, in our context, because there's a couple of different implementations of this that exist, verifiable encryption takes essentially a transparent block of data, is provided with a an encryption key, which is asymmetric cryptography based. So there is a corresponding decryption key. The encryption key is a public key, the decryption key is a private key. You may not necessarily own this. So for example, in Q, for Quilibrium Inc., and we're providing the S3 compatible API, we're not thinking about this in terms of us managing keys for the users. We do not want to manage your keys. Like, we do not want to know your keys. And so by consequence, that means that in order for you to actually, securely provide that data, it has to be encrypted in a way that the network can handle it, but then also know that we haven't done anything screwy to that data. So say, for example, if you were just transparently giving your data to Amazon Web Services and you're using their KMS service in order to actually encrypt that data, you are trusting that Amazon is not using the KMS services that they're providing to potentially store other data on your behalf, saying that you stored it. Or alternatively, that they are actually not storing the data and that they're modifying it in some way that you won't be able to retrieve it in the future. Or that they're providing that data in a way that it is accessible to external authorities. These are all things that we do not want to do. We don't want to even be capable of doing it. So when you talk about the divide between don't be evil versus can't be evil, this is one of the ways in which we do this. So when you do verifiable encryption, you are providing two important things that are publicly seen by the network, and then there's private things that of course relate to your data itself. The first is you're creating essentially the encrypted output, of course, because it is encryption at the end of the day. And then, which is just basically an opaque blob from the perspective of somebody who sees this output. Like, what, if I wanted to know what that data was, I can't infer that from the encrypted output. And then from the other side of this, in order to ensure that, for example, Quilibrium Inc. is not doing something screwy with your data, we would then also have a corresponding component that you're creating when you upload this data through the S3 compatible API. You're creating a secondary element, which is the proof. And this proof is a zero knowledge proof that essentially determines, was this data encrypted correctly such that it is decryptable by the corresponding private key to this encryption key. So those are the two outputs that come out of this, and it's very succinctly verifiable so that any node that operates on the network knows that this is correct. Okay, so now we have our file, we've broken it down into the pieces, we've created the requisite verifiable encryption objects that are the outputs, and then we need to put it into the set of vertex adds. So let's call this one v1, and call this one v2. Oops. So these then end up, sometimes I struggle with Excalidraw. These two things end up added to the sets of vertex adds. But what's important to know is these are added by reference. So we essentially have what is called the statement element, which relates to the overall data that comes through for the proof. That statement is what gets encoded into the Hypergraphs vertex adds. The actual underlying data to it is stored separately in the log structured merge database. And these two vertex adds objects are essentially now contributing to the overall proof tree. So each of these sets, these two-phase sets, are individual proof trees, these Verkle proof trees, if you will, such that you end up, if there's really only two objects, then there's only two objects, but so that you end up with, for the overall application of the network, the overall application shard of the network, I should say, you end up with a singular root commitment that collectively is a statement that can be used to verify any data on the network. And in this case, at the application level. So when we're talking about this shard-based approach, obviously you don't need a shard when you're dealing with just these two items, but for example, as we've been doing on testnet, we've been creating a very, very massive application level shard for the token application, as we've been encoding mainnet data onto testnet to verify that we can safely do this upgrade to 2.1 for mainnet. And as part of that process, we have generated a very, very massive application level shard for the vertex adds sets. And so what ends up happening is you end up with a tree with a lot, oops. Okay, there we go. You end up with a tree with a lot more, not just leaves, but branches. And again, keep in mind that the maximal number of these elements is not 4, as this picture would suggest. It's up to 64. So you end up with a very deep set of branches and then underlying leaves at the bottom of it. And so how we dictate shards are created from this is going back to the original point that was made about how data is split out. A vertex can only be up to 1 gigabyte of overall data. And that is determined from, again, that statement information that's been provided. That statement is an encoding, basically a non-reversible encoding of the underlying data that's being encrypted, and it's used for the basis of these proofs, but it's also telling us how much data is being encoded. We are storing these in blocks of essentially 54 byte segments, and so that collectively gives us a number that we can keep rolling at every branch level of the tree when things are being inserted or removed, but in this case it doesn't quite work like that. We just do additions. And then the second set for vertex removes is where the actual removes occur. But we essentially have these leaves of the tree that then roll up their size to the branch, that then rolls up their size to the next branch up to the root eventually. And that gives us the information we need to know in order to determine how much data has been stored under that application. But consequentially, we then also know, in this case, because we have 2.75 gigabyte entries, that the logical shard itself falls under the individual leaf. And the reason for that is because a prover is expected to maintain up to 1 gigabyte of data that is being proven over for any given shard that's logical. So, for example, if I have a bunch of 54 byte entries that are all unique elements that are unrelated, but they all fall under the same series of branches, and it collectively is less than 1 gigabyte, you can still reasonably prove over that data all the same. And you would be covering a lot more data. But what's important to think about from the perspective of what people run these nodes for is, of course, the rewards. You would be getting a reward relative to the overall data that you're proving out on the network. And there are intrinsic, computational limitations to how much of these individual proofs, obviously, one machine can produce, which is why we have separate workers. So when you think about it from that perspective, you think about the logical structures of proofs would be roughly chunked up to 1 gigabyte of data in the most simple case. And then we have this concept of multi-proofs where there's sometimes many branches of data that collectively is more than 1 gigabyte, or individually they're less than 1 gigabyte, but collectively they're 1 gigabyte or more. And from there, the workers can produce proofs at a larger level of the branch, and that gives them the ability to prove over more data and earn more rewards. So when we talk about our existing structure and how 2.0 works and how it relates to how shards are done on 2.0, there isn't. There's only one shard on 2.0. It's the core data proofs that are coming through the frames. There's only one actual commitment that all of these workers, that all of these miners with the workers are operating over. It's just one singular segment of data. And they don't have to maintain that data. The workers are just fed that particular bit string, and then it produces the proofs, feeds it back to the master, and then the master emits their own proof in order to obtain rewards. That's what's changing. That's what's migrating over into 2.1. When we're talking about this combinatorial of 256 and 3, that's actually the global commitments level. So the different levels of global commitment shards that are being performed, and then deeper into the application and data level shards. Instead of having a master that is sequencing all of this, because this would be a lot of data for an individual master process to be sequencing for all of the workers are instead responsible for sequencing their own collective shards that they are managing, which results in this scenario where you have a master, it's comprised of a few workers, and then the master is it's aware of which specific sets of shards it's covering based on whatever allocation strategy it uses for trying to accumulate rewards. And then it can provide those proofs, but it's never actively managing them quite in the same way where everything is convergent around the master node in 2.0. So those are the distinct properties that essentially differentiates 2.0 from 2.1 and how that relates to how shards on the network are created. Now there's one thing I left out here with respect to how this data relates to the hypergraph. Obviously it's a hypergraph. You can have hyper edges, and in the case of how we're doing S3, I left out the other piece. The other piece here is that the hyperedge adds a set of the app-specific shard of the hypergraph is what actually relates the files together. So I've created these two entries, and I need to make sure that I can relate to them as a singular entity. And so I create a hyperedge that links those two vertices together under the rules of the application. And that essentially gives you a unitary object that you can query and obtain all of the vertex addresses you need in order to surface that file. Finally, the last piece that I wanted to talk about was how this hypergraph is oblivious. Because obviously, it sounds like I've got a very basic data drilling structure in place. How do I ensure that a node that I'm requesting for that data isn't aware of what data I'm actually requesting? And if you've seen my earlier videos talking about oblivious transfer, you would know kind of the core concept of how OT works, but it doesn't really immediately and obviously map over to how OT works for the hypergraph. So instead of doing this in a 64 span basis, we're just going to do this in a simple binary tree basis so that it's easier to reason about. And essentially, when you're querying data on a particular aspect of the hypergraph, you generally are you're setting yourself up for a specific security bar. You're basically having to answer a few questions up front, like, do I want the network to know which application I'm dealing with? Do I want the network to know which data shard I'm dealing with? What is my acceptable level of privacy when I'm querying for data on the network? And so based on that, you're going to choose either to do this search at the global level, which is very expensive, but sometimes is important, or you're going to do this at the application level, which is much more common because if there's enough users of an application, it doesn't really matter. And so from there, that special magic trick that is oblivious transfer turns into a collective series of prompts that is evaluated to essentially choose the ultimate underlying vertices. Now, what is considered to be the oblivious RAM-based approach is where you basically have the query processor processing all of the underlying entries, and that's just the naive answer. If I run through all of them and give you all of the answers, then I can't know which one you asked for, but that's really expensive, not just computationally, but in terms of overall bandwidth usage. And so instead, we have a hierarchical compact query evaluation, and that is essentially trying to establish a certain statistical bar for how many elements can we query for based on the overall size of the set and based on the overall paths it's taking on this underlying tree that it's evaluating through. So for each step, there's a back and forth where we are saying, if it's this bit, take the left one. If it's this bit, take the right one. But that actually is given for potentially both sides of those branches. And in doing so, it means that the server is going to send back at least some more data, but not the whole amount of data. It's just some more data that essentially provides a statistical privacy bar. And you essentially run that through, and you end up with a few different traces down the tree so that you have enough data points that efficiently tells you what data you were querying for, but doesn't tell the node that's doing the evaluation of that query what data you actually did query for. And so that's basically it. From the perspective of how this all relates into each other and how this is all partitioned out, it's nothing novel. These things have all been done before. They just haven't been done in this way. And from this global sequencing of data, when we're only collecting just the overall global commitment shard proofs just at that 19 kilobytes of data level globally, and that's what's getting sequenced by the masters, that's how we end up with a scenario that we're able to do a significantly larger amount of parallelization of processing and storing data on the network. Do it in a way that is securely provable, but also do it in a way that is significantly more scalable than any blockchain could ever be. And that's what we've been building up towards, and that's what's coming out with the 2.1 release. So I hope that was helpful in walking through these things. I'm going to give folks a brief opportunity to ask more questions as now that we're at the end of this, and If there's anybody that does have any questions, I'm happy to answer. Otherwise, that about wraps things up. And like I said earlier on the stream, this Sunday we will be returning to the S3 and KMS APIs and talk about QConsole. Thank you. I may not sound like it, but I actually do feel better. I just don't sound great. That's kind of the downside of the flu, but at least it's virtual, so I'm not getting anybody else sick. Let me double check if there were any questions over Twitter. It seems that Twitter did a weird thing, and I don't know if it actually... Okay, there we go. Cool. It doesn't look like there were any questions there. So, yes, thanks again for the well wishes. You had a question about not too late to get into Quill as a contributor. Yeah, no, it's an open source project. Like, if you want to just contribute to the project, you're more than free to contribute to the project. You can just go to GitHub for it, and let me post the link here. I just realized I was about to type it into a window that it wasn't going to send from. Any aspect of our underlying network and all the applications we build on it, like Quorum, for example, are open source. We strongly believe in open source. And the way we set things up and walk the walk and talk the talk is specifically to ensure that, the other side of the don't be evil versus can't be evil. A lot of companies will be pro open source at the beginning, and then they'll end up invoking some sort of loophole that lets them become like open core, maybe, but with a business license. We don't do that. That's the reason why we don't have a contributor license agreement. It's the reason why we're licensed as the AGPL. It ensures the fact that we could never do this, because we would then have to follow up with every single contributor who's ever contributed and make sure they agree to it, which they of course will not. So it's essentially something that keeps us honest as well as a company. Cool. Well, if there's no additional questions, then we can go ahead and wrap things up from here. As always, we try to keep these on every Sunday. Obviously, this was a bit harder with the flu, but this upcoming Sunday, we will return to the QConsole, S3, and KMS APIs, and also hopefully a few more interesting bits of news as we get there. So thank you all for watching, and I will see you next Sunday. All right.